Hey, folks. Alright, well, dark matter is really mysterious, right? Because why? Because it's matter. It has mass, it exerts gravity, and yet you can't see it in your telescope, right? It's not called dark matter because it's black. If it were black, you could see it in telescopes in the sky. It is transparent. It's invisible to telescopes. We call it dark kind of because we're in the dark about it, because it's mysterious. And even to this day, we're still trying to figure out exactly what dark matter could be. But one of the big pieces of evidence that's going to lead us to figuring out what dark matter eventually is studying where dark matter is, how much dark matter is there, and where is it distributed in space. That'll help us narrow down which of the possible explanations for what dark matter is makes the most sense. Right? So that's what you're doing here, is you're saying, okay, well, we know that, Newton's version of Kepler's third law is true for any orbits. Right? It's true for planets orbiting the sun, for moons orbiting planets, or for our purposes here, stars orbiting around the galaxy. They will all orbits abide by Kepler's three laws. But the big innovation with Newton's version of Kepler's third law is that the mass is important here. That the mass will determine what the period of an orbit is at a given distance, at a given orbital distance. Remember, what is the semi-major axis? It's the average orbital distance. It's the average orbital radius. The period is the time for one orbit. And in this formula, the mass will be the mass enclosed by the orbit measured in solar masses. Let me just say that again, and let me draw a little illustration to hopefully make some more sense here, right? If you've got, well, in this case, if you've got our solar system, right? You've got the sun, right? There's the sun, and you've got a planet orbiting there. Let's say this is Earth. Okay. The mass here, the mass in this equation, or in this equation, they're the same equation, right? The mass here is the mass that is enclosed inside of the orbit. The mass that is enclosed within this orbital radius. So if you're just talking about the Earth orbiting the sun, then what's the mass enclosed by the Earth? What's the mass inside of Earth's orbit? It's just the sun. I mean, yeah, there's also the mass of Mercury and the mass of Venus, but those are tiny compared to the sun. So it's one solar mass. And then if we jump out to, well, let's say Mars, right? If this is the orbit of Mars, then Mars is farther from the sun, but the mass enclosed inside of this orbit is the same. It's still just the sun, right? Just because you moved further from the sun doesn't mean you've added extra mass inside of Mars's orbit, because there's not that much in between the orbits of Earth and Mars. So if the mass is the same, or well, you know what, we'll do this first problem here, right? If you're using Jupiter, right? Jupiter has a semi-major axis of 5.2 AU, and Jupiter orbits the sun in 11.86 years. So what is the mass enclosed? What is the mass enclosed inside of Jupiter's orbit? Well, we can do that math. We programmed our spreadsheet for Kepler's laws to do this before, but remember, let's see here, make our lives easier here, right? That the mass is the semi-major axis cubed divided by the period squared. So Jupiter orbits the sun at an average distance of 5.203 AU. Remember, this has to be in AU in order to work. the period of the orbit has to be in years, and then you measure the mass enclosed by that orbit in solar masses, right? Jupiter has an orbital period of 11.866 years, and then the mass is what? The mass equals the semi-major axis cubed divided by the period squared. Well, surprise, surprise. The mass that is enclosed inside of Jupiter's orbit is one solar mass. Of course it is, because the mass inside of Jupiter's orbit it's just the sun. Right, so, one solar mass it is. But of course we can rearrange the algebra like this to say, all right, what if the mass doesn't change? Like, say, in our solar system, right? If the enclosed mass doesn't change, right? The mass inside of Earth's orbit, inside Mars's orbit, inside Jupiter's orbit, it's just the sun. So if the mass, as you get further away from the sun, the mass stays the same. So if your orbital distance increases, well, then the period's going to increase. Right? The farther away you are from the sun, the more time it takes to orbit the sun. So what happens to the period? As the distance increases, period increases also. But if the orbital period gets longer, if it takes more time to orbit the sun, then it must be because you're moving slower. So what happens to the orbital speed? The speed decreases. If it takes you longer to travel a distance, if you're traveling a certain distance, say around the sun, but it takes you more time, it must be because you're moving more slowly. So that's what happens in our solar system, right? As you're traveling away from the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, right? As the planets get further and further from the sun, the enclosed mass, the mass inside that orbit doesn't change. It's one solar mass all the way out into the solar system. And so then as the planets get further from the sun, they have longer periods and they're orbiting slower. And so as you get further and further from the sun, the orbital speed goes slower, 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 slower. This is what you call Keplerian motion, right? The Keplerian motion is the motion of, well, originally it was the motion of planets around the sun and how they get slower as you get further out. Now, let's talk about a more complicated system like galaxies. If you're talking about the speed, the orbital speed of stars around the galaxy, then things get a little more interesting. Why? Because let's flash back to the Milky Way microtask, right? If you look at our galaxy doesn't have just one object with all the mass, right? The mass of our galaxy is spread out over lots of stars and lots of gas. Sure, there's the supermassive black hole in the center, but the supermassive black hole in the center, I mean, it's a supermassive black hole. It's got a mass of a couple million solar masses, but the whole galaxy has hundreds of billions of solar masses. So it's crazy to think that there's a supermassive black hole at the center of our galaxy, and yet all that mass doesn't amount to much. Once you add up all the mass of stars and gas, there is way more mass in stars and gas in our galaxy than there is in the black hole in the center. Right? So this mass is all spread out. But remember that the orbital speed depends on, so the orbital speed of a star orbiting around the center of the galaxy, or orbiting around the galaxy, depends on the mass that is enclosed within that orbit. That's why the graph of speed looks like this. You know what? I'm going to fold this real quick so we can look at both of them side by side. Okay. All right. This is the orbital speed of the stars versus distance from the center of the galaxy. So here's the center of the galaxy, and then we're getting further and further out. Right? If you are, well, there's no other questions on this page, so let's jump over to this one here. Right? If you're at the center of the galaxy, right? If you're a star at position A, you're at the very center of the galaxy. If you're at the very center of the galaxy, there's not very much mass enclosed, right? You are at the center. There is no mass that is closer to the center of the galaxy than where you are. And if there's no enclosed mass, if there's no mass inside of your orbit, then there's no gravity to pull you into orbit. So you're just sitting there, right? A star right at the center of the galaxy, or let's say a black hole at the center of the galaxy, it's not orbiting. It's just sitting still at the center because there's no enclosed mass to pull it into orbit. But then by the time you get out here to B, right? B is the outer part of the central bulge, right? Once you're out here, all of this mass is closer to the center of the galaxy than you are, which means all of this mass is pulling you around, so you're moving at a pretty fast orbit, which is why as you get from the center of the bulge out to the edge of the bulge, the speed gets faster and faster and faster, because as you go from here out to here, there's more and more and more mass closer than you are, enclosed within your orbit, pulling you to go faster. So that's B right there. B is the edge of the central bulge. But then once you get out here we go again, black on black. You know what? Here we go. I'm going to find a white pencil one of these days. All right. So once you get out here, in the gap in between the arms, you're getting further and further from the center of the galaxy, but if there isn't that much stars and gas out here. There's not none, but there's not as much stars and gas in between the spiral arms. And so as you go from here further out, you're going to slow down because you're getting further from the central mass of the galaxy. And so that's why there's this dip. This is the speed of stars in between the two arms. Slows down a little bit. But then you get into the second arm, the second spiral arm, right? Here's the first spiral arm. You're going really fast, and then it slows down, and then it speeds up again, right? As you get into the second spiral arm, now there's a bunch of more stars and gas inside your orbit, and that's going to pull these stars to go a little faster. And then as you get further, because our solar system, right? Remember, our solar system is right there, right? Our solar system is kind of on the outer edge of the second spiral arm, so this is where the stars are getting a little further out in the inter-arm space. They're going to start slowing down again. So that's why, okay, here's the second spiral arm, and then things are going to slow down as you get further and further again. And then, kind of out of frame here, out of frame of this picture, you've got another arm that goes out here, and then the stars speed up again in that third spiral arm, the one that's just petering out right there. And that's where, like, okay, this is all making some sense, right? The graph of speed versus distance flattens out because, sure, as the stars get farther from the center, they're farther from the center of the galaxy, so their semi-major axis increases, but also the amount of enclosed mass increases. So those two effects kind of cancel each other out a little bit, and therefore these stars all move at the same speed. But once you get out here, once you get out past the last spiral arm, there are stars out here. Not as many, but there's still some. Out here, you're out beyond the disk of the galaxy, which means as these stars get farther and farther away, there's not much more enclosed mass. If, you're basically adding up the whole mass of the galaxy at this point, and you're just getting further from it. So that's where the stars should start behaving with Keplerian motion, I should say. If we have maxed out the enclosed mass, if we've added up all the mass of the galaxy, then as the stars get farther away, they should slow down, just like how planets slow down when they get further from the sun. But that's not what happens. Right? Out here toward the outer edge of our galaxy, these stars don't slow down the way Uranus, Neptune, Pluto slow down toward the outer edge of our solar system. That's one of the big pieces of evidence for the dark matter, right? The fact that as you get further from the center of the galaxy, the enclosed mass doesn't stay the same. As you get further, the enclosed mass also increases. So that the speed of these stars, the speed of the stars doesn't slow down. In fact, they kind of speed up. So there's something out here. There is some halo of mass surrounding and, inside and around our galaxy, so that these stars at the very outer edge of our galaxy, they're still moving at the same speed, or even a little faster, because of the extra mass that we cannot see in our telescopes. If all of the mass of our galaxy was stuff we saw, stars, gas, dust, normal stuff, then the orbital speed of these stars would slow down. The fact that they're going faster means they're being pulled by more mass that we cannot explain from stars and gas and dust and normal matter, so it must be some weird invisible matter that's not showing up in our telescopes. That's the dark matter. So, let's look at these letters here, right? A is the center of the galaxy, right? B is the edge of the central bulge. So, A here, A is the center of the galaxy, right? B is the edge of the central bulge, right? Then there's the dip, and then C is the first spiral arm. D, and there's the dip. D is the second spiral arm. And then out past D is where the Keplerian motion should but doesn't happen. And so out here, where there's all this extra mass pulling these stars faster, that is the dark matter dominated region, right? Now, there is dark matter inside the galaxy, right? There's dark matter in between, in the stars and the gas and in the interstellar medium space also. But it's out here at the edge where the normal matter fades away and the dark matter shows itself more prominently to pull these stars faster. So this is the dark matter dominated region out here at the edge of the galaxy, out in the E region. So this is the dark matter dominant region. All right. So like I said in the video, right? If we just saw this in our galaxy, maybe you could chalk this up to, it's hard to make measurements of our galaxy when we're buried inside of it. Maybe there's something weird going on. But the fact that we see this in all spiral galaxies says, oh, no. The dark matter is real and it's in all spiral galaxies. How much of it is there, though? Well, we can figure this out here, right? How much enclosed mass is there inside of Earth's orbit around the sun? To go back here, right? If the orbital period of the sun is 230 million years, so I'm going to say 2.30 E 1, 2, 3, 4, 5, 6, 7, 8, right? 2.3 times 10 to the 8 years. And the orbital distance, the orbital radius of the sun around the center of the galaxy is 8,000 parsecs. But 1 parsec is this many AU, and we need the semi-major axis in AU in order to use Kepler's third law. So I guess we'll do some math here. What is the orbital distance? It's going to be 8,000 parsecs times the number of AU in 1 parsec, 206,265. All right, so that should be, let's change that into some scientific notation to make it easier to read. Okay, so our sun is 1.6 times 10 to the 9 AU from the center of the galaxy. So we're 1.6 billion AU from the center of the galaxy. And when you plug those in, yeah, there we go. So the mass is, the distance of the sun to the center of the galaxy is 1.65 times 10 to the 9 AU, which means that the amount of mass enclosed inside, so the amount of mass around the sun's orbit, the amount of mass enclosed within the orbit of the sun around the center of the galaxy is what did we find? 8.49 times 10 to the 10 solar masses. So basically, what is that? 84 billion, 85 rounded up to 85 billion solar masses? Okay. How much of that is dark matter? Well, how much of that? Now, that mass, that's all the mass. Right? So that's the mass enclosed by Earth, the sun's orbit of the galaxy. That's the mass of stars and the mass of gas and dust and the mass of dark matter. How much of that is dark matter and how much of that is stars and gas? Well, you have to measure the amount of stars and gas. And it's mostly, right, when you're in close, when you're near toward the center of the galaxy, which we're not in the center of the galaxy, we're out like halfway to the edge. But most of this is stars and the interstellar medium, right? It's when you get really out far from the disk, out toward the edge, where the mass of stars and gas stays constant, and then the extra mass is coming more from the dark matter than from the normal matter. So that's why we say, okay, out here is the dark matter dominated region, not because there's less stars, but because the number of stars enclosed has stayed constant, and the extra mass comes from, all of this extra mass, that's the dark matter. Okay. All right. That was a lot. So hopefully that's making some sense. Post your questions if you have them. And if that's making sense, then we can extend this to be looking at other galaxies and, where's the dark matter in other galaxies and where's the dark matter in the rest of the universe. So we'll pick that up with the next assignment. Have a good one, everybody.